Great. How's the mic? Can you hear the mic?
Our next speaker is Jane, and she's going to tell us about agnostic proper learning of monotone.
Thank you. This is joint work with Arsen and Vasilyan. We're both students of Rubinfeld at MIT. This is a talk about a topic that at first glance seems to have nothing to do with graph simplification. I'll tell you why it does in a bit. So we're in the setting of agnostic proper learning, which means that we're getting random examples we're getting random examples x comma f of x. That's not necessarily from the concept class C, it's some distance away from the concept class. We're gonna call that distance opt. Then we're gonna run a learning algorithm and output some hypothesis, and we require that the hypothesis belong to C. This is what makes it proper learning rather than just learning in general. And we want the error of f, or the error of our hypothesis with respect to f, to be opt plus epsilon. So we can think of this as the task of finding the closest function in the concept class C up to the additive error parameter epsilon. And just as a note that for this talk, we're always going to be using the uniform distribution over the Boolean cube. So it's the probability over uniformly random x that f of x disagrees with g of x. So first I will set up the problem and give some background on what's already been known about it, and then talk about two key ingredients of the algorithm, and then put it all together. And this step about using local computation algorithms as an ingredient for the learning algorithm, this is the graph simplification part. We'll see why in a bit. So first, our concept class is the class of monotone functions on the Boolean cube. This means that if x is smaller than x prime, so the set of 1 bits in x is a strict subset of the set of 1 bits in x prime, then f of x has to be at most f of x prime. So that's what makes a monotone function. So for the agnostic learning task, our task is to take samples from a function that is opt close to being monotone, and then output a monotone hypothesis whose error is opt plus O of epsilon. Here's some related work on anything to do with the concept class of monotone functions. Not exhaustive at all, but people study this in the context of property testing and reconstruction, and also learning. So here's our main result. It's just the existence of an agnostic proper learner. Well, constructed, we give the algorithm. This is an algorithm that runs in time 2 to the square root n, given uniform random examples, and outputs a monotone function that is, outputs a monotone function whose distance is opt plus O of epsilon. 2 to the square root n is always the running time we're shooting for. So if I say efficient in this talk, efficient refers to 2 to the square root n as opposed to 2 to the n. Previous best running time is 2 to the omega of n for this problem. And I'll explain what that comes from in a bit. And also, any agnostic learner can be used as a distance approximator with additive error. So if you're interested in the question of approximating the distance of f to the nearest monotone function, you can do that by learning this proper hypothesis and then estimating the distance from f to the proper hypothesis. This nearly matches an information theoretic lower bound for learning monotone functions with membership queries, which also takes 2 to the omega of square root n. This holds even in the realizable or non-agnostic setting, and even for improper learning. And the bounds, I call it nearly matching because technically the lower bound doesn't apply for very small epsilon, but for all epsilon to which the lower bound applies, the bounds are matching, up to constant factors in the exponent. So previously, an improper learner was already known for quite a long time. This is by Bshouty and Tamon. It's the low degree algorithm. They showed that every monotone function is 1 minus epsilon concentrated on Fourier terms of degree at most square root n. So this yields an improper learner where you learn the low degree approximation, you output the sign of a polynomial. The polynomial has 2 to the square root n terms. This can be made agnostic, but it's not proper because this sign of a polynomial, even though it's opt plus epsilon close to the target function, is not necessarily monotone. This immediately yields a sample efficient algorithm, but it's really, really time expensive. What you do is you learn the improper hypothesis and then you enumerate all the monotone functions and pick the closest one. But we want to make it time efficient as well. We also already knew of a semi-agnostic proper learner. This is our previous work with Ronit, where we learn the improper hypothesis and then as a black box correct it to monotone. However, this blows up the error from opt+ε to 3 opt+ε, and anytime you have a constant factor greater than 1 in front of opt, it's semiagnostic learning. So this approach of learning an improper hypothesis and then correcting it to be in the concept class as a black box is inherently blocked at 2 opt. It must be semi-agnostic. If you think about it, like f is opt far from monotone, so your improper learner is allowed to learn a hypothesis that's both opt far from f and opt far from monotone. And so even if you find the exact closest monotone function to that hypothesis, you could modify it by opt and get a monotone function that's 2 opt away from f. You correct it in the wrong direction away from f. So in order to get an agnostic learning guarantee and get rid of this 2, we need to not make the improper hypothesis a black box. We need to improve the improper search to find a hypothesis that's both opt+ε close to f and epsilon close to monotone, rather than opt+ε close to monotone. Then when we do black box correction, we can only inflate the error by a factor of epsilon, and that's good. So now we'll get into the ingredients for the agnostic learner, the first being convex optimization. This requires a reframing of the learning problem as a convex feasibility problem. So recall that the goal is to find a polynomial that's opt+ε close to f and epsilon close to monotone. We're going to be optimizing over the space of low-degree polynomials with real values. So we're relaxing from Boolean-valued functions to real-valued functions and use L1 distance instead of Hamming distance. And then we can observe that the set of polynomials that we are looking for is a convex set. We can verify that monotone functions are a convex set, like mixture of monotone functions is still monotone. We're taking an L1 ball around a convex set and also an L1 ball around a point, and we're taking their intersection, so it remains convex. However, the number of constraints that define this set is exponential, 2 to the n. So what we want to do is use an optimization method that doesn't depend on the number of constraints and instead only depends on the dimension of the optimization domain. So we're going to use the ellipsoid method because its running time is polynomial in the dimension of the domain, which is 2 to the square root n. Yeah. The number of monotone functions, it's like 2 to the n, basically. Yeah.
Constraints 2 to the omega
n? Oh, because it's like monotonicity, you can think of it as a constraint on each pair of vertices. So like for each pair of vertices where x is comparable to y, f of x is smaller than f of y, yeah. And that's 2 to the 2n. Yeah. Okay, so yeah, what the ellipsoid algorithm requires in order to have running time that's smaller than the number of constraints is that we need to be able to give a separation oracle for the feasible region. So the way that this works is that the separation oracle takes in some point. So in our case, all of these points are polynomials, low-degree polynomials, as a query. And if the point is in the feasible region, this purple region, it'll output yes. Otherwise, it'll give a hyperplane that separates this point from the feasible region. And in our case, this hyperplane is going to be another polynomial such that the inner product of that polynomial with anything in the feasible region is low. So any monotone function that's close to f has low inner product with this, but this bad queried point that's not feasible has high inner product with the separating oracle. So in a way, you can think of this as a property tester with extra guarantees. It's a property tester where if you're far from the property, it gives you a witness. So giving a separating hyperplane for a point that has too high of error from f is easy and known, but giving a separating hyperplane for a point that's too far from monotone is something that previously hadn't been considered. So a key observation in this work is the fact that functions that are far from monotone have a large matching in the graph of monotonicity violations, which is something I'm about to define. And this is a witness for the distance to monotonicity. And this matching, if we can find a way to represent it efficiently, can be used to produce a separating hyperplane. So here's the violation graph. We'll put an edge between x and y in the hypercube if x is smaller than y and f of x is greater than f of y. So x and y are violating monotonicity with respect to f. The weight of the edge is the magnitude of the monotonicity violation. So in this case, like the weight of this edge is 0.5. And we're also only going to consider vertices that have Hamming weight within square root n or square root n log 1 over epsilon of n over 2. So this is like a 1 minus epsilon fraction of the hypercube, but the degree of the violation graph is 2 to the square root n rather than 2 to the n. This will be important because we're going to run graph algorithms that depend on the degree. And we're going to search for an approximately maximum weight matching in this graph to serve as our witness that we're far from monotone. The witness will be, remember, the witness has to be a polynomial. So we're going to define a distance witnessing function, m of x for each x. So if x is not matched in this maximum weight matching, then m of x is going to be 0. Otherwise, if x is matched, or for each edge in the matching, we'll set the top vertex to be -1 and the bottom vertex to be 1. So we can now observe that the inner product of m with f is exactly the weight of the matching, but it can't have positive inner product with any monotone function, because for any monotone function, this top vertex is going to be bigger than the bottom. So inner product will always be negative, or non-positive. So suppose you can evaluate m of x quickly for an arbitrary x. M of x is a function. It's a bounded function from the hypercube to this interval -1 to 1. So if you can evaluate m of x quickly for an arbitrary x, you can learn an approximation to it. And if you can learn a low degree approximation to m, remember that f itself is low degree. So taking this low degree approximation will preserve inner products with f. And since we know that the inner products with m satisfy the right properties, this gives us our separating hyperplane. So what's left is to find an algorithm that evaluates this function m of x quickly. And that brings us to our next ingredient, which is local computation algorithms, aka graph simplification. So local computation algorithms, these are algorithms that read small portions of a large input and also output queries to small portions of a large output. So it's something that can answer user queries to the output without storing it explicitly. And an alternative way to think about it, which is kind of the way it's used in this work, is that it's something that transforms a succinct description of the input into a succinct description of the output. So as an example, suppose you have a circuit that computes the adjacency lists of a graph. So you put in the identity of a vertex into this circuit and outputs a list of its neighbors. This is a succinct representation of the graph, because it doesn't store the entire graph, it's just a circuit that computes the adjacency list. Then, if we have an LCA that's a circuit of size t, then we can output a size s times t circuit that computes, for example, if the LCA is for MIS, that computes membership in the independent set. So now you feed in a vertex x, and you learn whether or not it's in this particular maximal independent set. This size is s times t, because you can think of it as taking the circuit for this LCA, taking every query, every adjacency list query, and plugging in this circuit into that query. You get s times t. So we use LCAs for two things. One is to get this approximation to the maximum weight matching. This is for computing the distance witnessing function that I talked about a few slides ago. And the other is that once we return a hypothesis, once the ellipsoid algorithm returns a hypothesis, it will still not quite be monotone. It'll be epsilon far. So then we need another LCA that's a local corrector for monotonicity so that we can output a monotone hypothesis. Both of these are built on an LCA for maximal matching that runs in polydelta time. That's why we care about the degree, because polydelta is going to be 2 to the square root n. So for the approximate maximum weight matching problem, we give an LCA that runs in delta to the log 1 over epsilon time for 2 approximate maximum weight matching. And so when you run this in the violation graph, because delta is 2 to the square root n, this gives us a 2 to the square root n time evaluation of the distance witnessing function. And then the other LCA that we give is this real-valued monotonicity corrector, which I'll state here because I think it's independently interesting. So let f be some real-valued function that's alpha close to monotone. In our setting, alpha is always going to be epsilon. But for arbitrary alpha, if you're alpha close to monotone, then there's an LCA that makes queries to f and outputs queries to g such that g is monotone and the distance to f is alpha plus epsilon. So this will be O of epsilon when both alpha and epsilon are the same. The running time and query complexity are going to be 2 to the square root n with an extra log 1 over epsilon. And also, this LCA doesn't necessarily have to run in the hypercube. If you want to correct monotonicity for some function that maps vertices of a different poset and you want to correct it to monotone, this parameter will just be replaced with delta. It'll be delta to the log 1 over epsilon. It has another parameter. It'll be delta to the h log 1 over epsilon, where h is the longest directed path. So this local correction of real-valued functions uses as a black box a local corrector for Boolean-valued functions, which we gave in previous work. So in previous work, there's an algorithm that makes 2 to the square root n queries and outputs a way that you can swap labels in the hypercube, like swap the function labels of points, such that the swapped function is monotone. So for example, if this is your original function and this is your poset, then this algorithm will output that actually if you're this vertex, you should output the label of this vertex instead. And we reduce from correcting monotonicity on integers to correcting monotonicity on Boolean values by observing the following. So let's say that f is a k-valued function. So f can be like projected onto its k bits, or log k bits, f1 through f log k. And we observe that like an equivalent way to state that, that f is monotone in the k values is to say that f1 is monotone, and then for each fi, fi is monotone on the subgraph induced by vertices that agree on the values of all the previous more significant bits. This is a clunky definition. It's best to just observe it. So this is a 2-bit function, and you can observe that it's monotone in the values from 0 to 4. And like equivalently, this first bit is monotone. So the first bit is like 1 here and 0 here. And the second bit, if you just look at it by itself, it's not monotone because this would be a violating edge. There's a 1 here and a 0 here, but we're restricting to just the vertices that match on the first bit. So like on this restricted graph, it's monotone because it's constant. And on this restricted graph, it's monotone because it's increasing. So because of this way to state monotonicity in k values in terms of Boolean monotonicity, we can run suppose we're still in the integer case, you just run k iterations. So you like correct monotonicity in the first bit, and then within the set of vertices that agree on the first bit, correct in the second bit, etc. Then you end up correcting monotonicity for the whole k. So the real valued corrector just rounds to multiples of epsilon and then runs log 1 over epsilon stages of the Boolean corrector. And then to prove that this is correct in terms of preserving the distance to monotonicity, it's just true that any label swapping algorithm, so like any algorithm that works by saying take these vertices and exchange their labels, if it swaps only vertices that violate monotonicity, it can't increase distance to monotonicity. So now I'll put it all together and just say what the algorithm does. So we're running the ellipsoid algorithm on the space of low-degree polynomials. And suppose the first candidate is too far from f. The first candidate has like really high error with respect to f. Well, then we look at some labeled examples and output a witness that p was a bad predictor with respect to these labeled examples. Then it'll generate another candidate. And suppose that this candidate is close enough to f, but is too far from monotone. If it's too far from monotone, then we use our maximum weight matching LCA to estimate the low degree component of our distance witnessing function and output that as the separating hyperplane. And eventually, after enough iterations, it'll output a predictor that's opt close to f and epsilon close to monotone. Then we run our then we run our real valued L1 distance preserving corrector. And this gives us a monotone real valued function. And then there's one more step. That step is a randomized rounding step because we need to output a Boolean function. We output the rounded function, and that is our monotone hypothesis. And that's it. Any questions?
Sure, to the Boolean case. What's the reduction from real to Boolean?
From real to Boolean is first from real to integers, and then from integers to Boolean. So from real to integers, it's just rounding to the nearest multiple of epsilon, and then treating those as the integers. So like then multiply everything by 1 over epsilon. And then correct monotonicity on this integer valued function. And then at the end, round to Boolean again.
And that's where you get the L1 norm that appears. Because for Boolean, it's Hamming, L1, L2, they're all the same.
Yeah, so this integer valued corrector preserves L1 distance.
Any other questions?
Yeah.
So the monotonicity corrector is the correction LCA. It's solving a problem which is kind of similar to the problem you start with, right? You give it your hypothesis and you want to find a near monotone algorithm. Why is this problem easier than the one you started with?
Oh, because we're allowed to blow up the distance to monotonicity by constant factors. So like what's hard about the original problem is we want 1 times opt plus epsilon rather than like 2 times here. Yeah, so this is stated in terms of like this parameter alpha, right? And we're allowed to blow up alpha by constant factors. In the original problem, we're not allowed to blow up alpha by constant factors.
So the entire machinery around that is just so you get a constant.
It's just to get alpha. Exactly. Yeah.
So, what happens for improper realizable learning?
Improper realizable learning is the low degree algorithm. You output. Yeah. In the improper realizable setting, you learn the degree square root n coefficients and output just the sign of it.
No, this is agnostic, right? Like,
This is agnostic and also realizable. I mean, it's the same in both cases.
and also in your theorem 2, you're taking the Boolean-valued to real, right?
In theorem 2,
Yeah. So what happens when you take the domain to be real?
when you take the domain to be the real line. I guess so. I mean, this has to run on discrete domains, I guess, unless you discretize the domain. If you discretize the domain and make it like the real line with n vertices, then the degree should be n squared. So it would run like n squared time. Yeah.
Can you go to the flow charts?
Yeah.
So what exactly is specific to monotonicity? I mean, besides the fact that you have the building blocks.
What's specific to monotonicity? The fact that it's a convex set. So like when you take monotone functions over the reals, it's a convex set of functions. That is, I guess, not specific to monotonicity, but is a property enjoyed by monotonicity and not very many other properties. And then also this like local correctability and local witnessability. These are also, again, not particular to monotonicity, but not all properties have them, I guess.
Are there any other properties for which you have all of those?
Yeah, we're working on one for functions with low noise sensitivity, which has most of these desirable properties. And then people also kind of suspect that something should work for indicators of convex sets. That is not a convex set of functions, but does it have local witnessability? Kind of. We're not really sure what the complexity of that should be.
Okay, so let's thank Ian again.